Welcome, ladies and gentlemen, to our continuing study of how to show forces acting on an object. The tool that we use is the free body diagram, and you've drawn several of those. We want to continue that study. We're going to look at a few more examples today, one in particular in which there are angled forces. Up to this point, you've only looked at situations where the forces are vertical or horizontal. Today we're going to consider some angled forces. Before we do so, however, let's review just briefly what we covered before. Okay, we started with Newton's first law, and we learned that Newton's first law actually provides for two types of motion. We have two situations. We've got
the situation known as static equilibrium. All right, so static. Okay, when the forces are balanced and the object is at rest. We have the other situation, dynamic equilibrium, where the forces are balanced but the object is moving at constant velocity, which means constant speed and constant direction. So, and we did a few free body diagrams to that extent. So we've got these two here. These are our two motions, all right, right like that and like that. So we could either be moving at constant speed and in direction, or we can be at rest. If you remember, we actually, by looking at a free body diagram, we can't tell the difference between these two, because in both cases it just means that the forces are balanced. So you need a little more information about the motion of the object to be able to tell whether an object is actually moving or not. You need that information in addition to the free body diagram. Remember, just by looking at the free body diagram, you cannot tell the difference. Okay, remember that we show balanced forces simply by drawing arrows the same length. Okay, so if we take a simple example here, okay, of a box or a book on a table, right? The table's at rest. Of course, the table's at rest. The book is at rest as well. If I were to do a free body diagram for that, I would just want to make sure to draw my arrow that's going up, okay, which is the normal force from the table on the book by the table. I want to make sure that that arrow was just as long as the arrow going down, okay, which is the force of weight on the book by the earth. So in other words, I show balance in a free body diagram by paying attention to the length of the arrow. Now the fancy word for length of an arrow or size of a force is magnitude. Okay, please commit that word to memory. Students have a lot of trouble with it. It's a real easy meaning. Magnitude means size or amount. So the way that we show balance is we draw the arrows the same length. So the question is, what about in more complicated scenarios where the forces are angled? So I'm going to take a minute here. I'm going to pause the video and I'm going to draw one of the scenarios I'm talking about. We'll do the free body diagram together, and then I'll show you how to do the balance in one of those more complicated free body diagrams. Okay, you see on the screen now, you see a box that's on a slanted surface, and you see the statement here. We have a little bit of information about the motion. It says that friction prevents sliding. So that tells us a few things. It tells us that obviously friction's acting and that the box is not moving. Right? So we know that as a situation of static or dynamic equilibrium. Static it is. Okay. We're going to come over here and we're going to draw the free body diagram for this. Alright, so let's start here. We're looking at this free body diagram. We're going to make a dot. And of course, weight is definitely acting. Alright, so there's the force of weight. And now, you want to take a look here, and you can see that we have the surface is at an angle. So hopefully you'll agree with me that the surface is pushing on the block, but at an angle. What kind of force is that? You're right, it is the normal force. Okay, so let's draw that force. Okay, now
You might be wondering why I'm drawing it at an angle. Well, there's a good reason for that, and that's because the normal force is a perpendicular force. Remember, normal means nothing more than perpendicular, but it means that that force is always perpendicular to the surface, which in this case is at an angle because the surface is at an angle. Okay, coming back to the dot, we have one more. We have our third force, which is going to be friction, okay, and it is acting up the surface, opposing the intended motion of the block, which is down the surface. Remember, friction always opposes the intended motion. All right, so there we have our three forces, okay, and we want to label them. This one, let's go back to the beginning, right here, force of weight on the block by the earth, right? The earth is pulling a block down. That's what we call the force of weight or gravity. Coming up here, we have the force normal on the block by the surface. And then finally over here, we have force of friction on the block by the surface. All right, so now ask yourself, does this diagram look balanced? Because you know that the block's not moving, it's in equilibrium, and the forces should be balanced. You can see in this situation that the fact that the drawing's balanced is not so obvious. Okay, so I want to show you a method. I want to teach you a method. It's called the parallelogram method, and it is a way for you to ensure that there is balance in your drawing. Okay, so as the name suggests, it involves a parallelogram, and what you do is you take, in this case, we want to know whether these two forces that are acting upward, are they acting up enough to balance out the weight? Okay, and the way that you do that is you take these two and you just make them two sides of a parallelogram, and then you gently trace, okay, you gently trace out a parallelogram here. That is not the best parallelogram you've ever seen. And then the next step is to draw the diagonal. Okay, I'm just going to dot it. I'm just going to dot it in for you. Okay, and you can see that that diagonal is not quite vertical. Okay, now ideally, to show balance, this diagonal would be as long as the weight is. Okay, except it would be upward. So this diagonal represents the result of these two forces, normal and friction, acting together. And you can see that the way that I've drawn them is such that the diagonal of the parallelogram is not quite vertical. So what I need to do is I need to adjust the lengths of these two forces to make that diagonal vertical. Okay, in other words, what I need is, and this is going to get a little bit messy, but I'll clean it up in a little bit. I want my diagonal to go straight up like this. Okay, I want my diagonal to be like that, and I want, in other words, I want my parallelogram to look a little bit like this. Okay, like that. So you can see, and let me go in there and do a little erasing. You can see that, so that was the original one. I don't want this anymore. That's my original diagonal. I'm going to get rid of it. Okay, you can see that I need, in order for this dotted line to meet the friction force, I need to extend the friction a little bit. Okay, and that's exactly what I'm doing. I'm going to come back here, and I'm just going to draw this arrow a little bit longer, like that. Okay, so that now you can see that the parallelogram made by the friction force and the normal force creates a diagonal that's exactly equal and opposite the weight. All right, and maybe just a little cleaning up here, a little erasing, kind of clean that up, so you can see that this diagonal is equal and opposite of the weight. Now, honestly, it looks like the weight's just a smidgen long. Okay, so maybe we can pull that up a little bit so that it really looks like the weight is equal and opposite this diagonal, which is the result of these two. And that, ladies and gentlemen, is how you show balance in a free body diagram with an angled force. One last comment, and that is that these diagonals and these dotted lines are not real forces. So really, in the end, they should not be on your free body diagram. If you make them really light, okay, that would be cool, like a really light dotted line. or if you just make them really light and then after you've drawn your arrows, you erase them like I'm doing. Okay, so what I'm going to do here is just erase what I had drawn. Okay, so that, oops, I've kind of run into the F of the friction there. But basically, um, I don't want those dotted lines there in the end, right? I don't want them, at least I definitely don't want them confused for the actual forces. So this then is the final free body diagram. It's not any different than what you draw before. It's just 3 arrows with the 3 labels, but you used a little dotted system, the parallelogram method, to guide you in the drawing of the lengths of the arrows. So I'm just going to clean this part up here and then we'll be done. Okay, there you have it. I cleaned things up and that would be your final result.